We will now see the equivalent circuit of the single phase induction motor. So if you remember, the per phase equivalent circuit of the 3-phase induction motor, this was like this. The stator parameters R1 and JX1, the magnetizing component, this is the approximate circuit. There will be another resistance in parallel if you consider the core losses component as well. And then we have the resistance R2 dash by S, and finally JX2 dash. Okay, and this will be like this. This is the equivalent circuit, the per phase equivalent circuit. That means for each phase, this will be the circuit for a 3-phase induction motor. Now for a single phase induction motor also, it will be more or less similar, except that here we have 2 fields. What is that? One is rotating in the forward direction, other is rotating in the reverse direction. We have a double field theory, right? So according to that, this will be as it is same, R1 and JX1. Now the rest of the circuit will be slightly different. This you are going to write as JXM by 2. Okay, and this is similarly JXM by 2. And here you are going to have the circuit corresponding to the forward field. This is JX2 dash by 2, and the resistance value is going to be R2 dash by S into 1 by 2. Okay. Now here JX2 dash by 2 will be as it is. Now what about the resistance value here? It will be slightly different. Okay, because this is corresponding to the forward rotating field. Okay, so this slip that you have here, R2 dash by S, this S is the relative speed between the rotor and the rotor rotating magnetic field. Okay, but in the case of the reverse rotating field, it will be different. This is the reverse rotating field. So what is happening? If the rotor RMF is rotating at synchronous speed, it is rotating at synchronous speed, right? Rotor RMF. Now the rotor itself is rotating at what speed? At a speed n. Okay, now what is the difference between the two? Ns minus n is nothing but ns minus n, you can write as 1 minus s times the synchronous speed. So 1 minus s times the synchronous speed is going to give you s times the synchronous speed, right? This is the relative difference between the rotor RMF and rotor. Now understand that this is the forward rotor RMF speed. What will happen to the reverse rotor RMF? So you can write here reverse rotor RMF. This will move at a speed of ns only, but in the opposite direction. So you can also write as in the same direction, you can write minus ns. Okay. Now what about the rotor? Rotor is in the same direction, 1 minus s times ns. Now what is the difference between these two? The speed of this, you have to say take the same direction. If you take, you will have to subtract. If you are taking the opposite direction, you will have to add. So if you add, you are going to get ns plus ns minus s ns. So you are going to get 2 minus s times the synchronous speed. This is the relative difference in velocity with respect to the reverse rotor RMF and the rotor RMF. So the fraction of synchronous speed here is the s. Okay. So what is the fraction of synchronous speed here? 2 minus s times. Okay. So that is why this resistance we are going to get R2 dash by 2 minus s into 1 by 2. Okay. So this is the final equivalent circuit of the single phase induction motor. You have to remember one very important point here. We are not considering the auxiliary field winding here. We are talking only about the main field winding. Okay. So this equivalent circuit considers only the main field winding. So that means what will be the equivalent circuit during the starting? It will be completely different. Okay, this equivalent circuit will come into picture only when it has started running at the normal speed. So we will now see the power relations. For that we will draw this circuit once again. This is Jx1. Here we have Jxm by 2, Jx2 dash by 2, and what is the resistance value here? R2 dash by 2s. This is the forward field part of the circuit. And next we have Jxm by 2, here Jx2 dash by 2, and the resistance value is, this is for the backward field, so R2 dash by 2 times of 2 minus s, right? This was the equivalent circuit that we just discussed. Now often this part of the impedance, this is taken as Zf by 2, the forward impedance, the forward field impedance divided by 2, because all of these parameters are divided by 2. And what about this? This is the backward field impedance. So we write it as Zb by 2. So what will be the value of Zf by 2 if you take? This is equal to Jxm by 2 parallel to R2 dash by s plus Jx2 dash by 2. Okay. So whatever value you are going to get, you can write as the resistive part Rf you can write, but since there is by 2 here, we will write this as by 2 as well. Okay. Plus Jxf by 2. Similarly, we can write the backward impedance Zb by 2 as Jxm by 2 in parallel to R2 dash by 2 times 2 minus s plus Jx2 dash by 2. The resulting resistance and impedance you are going to get as, you are going to name it as Rb by 2 plus Jxb by 2. Here also you write the smaller f only, otherwise it will be confusing, right? So this is f and here also it is f. Now how can we write the power relationships? Power relations. What will be the expression for air gap power for the forwardly rotating field? This is going to be the main field winding current, square of the main field winding current into Rf by 2. This is the air gap power for forward field. Similarly, you can write the air gap power for backward rotating field. This is Im square into Rb by 2. This is the air gap power for backward or the reverse rotating field. So from here you can write the torque expressions as well. What will be the induced torque because of the forward rotating field? This will be the air gap power divided by the synchronous speed, right? We have seen in the 3-phase induction motor, the induced torque will be equal to the power that is produced, which is 1 minus s times the air gap power divided by the actual speed, which is 1 minus s times the synchronous speed. So you are going to be left out with the air gap power divided by the synchronous speed. Okay. So we have the forward rotating field as PGF divided by omega s. And what about the backward torque? The torque that is produced due to the backward field. This is going to be the air gap power due to the backward field divided by the synchronous speed. Okay. So these are the expressions for the induced torque with respect to each of the field. So what will be the net torque? Therefore, net torque will be equal to the difference between the two, the forward rotating torque minus the reverse torque or the backward torque. So you are going to get 1 minus omega s forward air gap power minus the backward air gap power. Okay, so this is the net torque that you will be obtaining. So these all, you can number these equations 3, and this is the 4th. Now we can also see the rotor copper losses. What is the rotor copper losses? It will be slip times the air gap power. So the rotor copper losses corresponding to forward field This will be what? S times the forward air gap power. Rotor losses corresponding to backward field will be equal to what will be the slip here? 2 minus S times PGB. So that means the net rotor copper losses will be equal to S times PGF plus 2 minus S times PGB. Now what about, this is the rotor copper losses. Now what about the converted power? Power converted to mechanical form due to the forward field. What will this be? 1 minus S times the forward air gap power. What about the power converted due to backward field? This is equal to 1 minus, slip is here 2 minus S. This into PGB. So you are going to get the net power converted to mechanical form. What will this be? This will be equal to 1 minus S times PGF plus, this will become S minus 1. So you are going to write S minus 1 times PGB. So you can simplify this as 1 minus S if you take common, you are going to get PGF minus PGB. This is the net power converted to mechanical form. So these are the various power relations in a single phase induction motor.